Solar updraft towers will have a role to play in solving one of today's dominant challenges: the global, sustainable, inexhaustible, and affordable supply of energy. The principle of this technology is relatively simple. The sun warms up the air within a cylindrical tube, and as this occurs, the external air is sucked through the tower and pushed upwards, thus converting solar energy into kinetic energy. This is done by the transfer of heat into physical motion. The convection within the tower causes a hot air updraft via the chimney or stack effect. The stack effect is, put simply, the movement of air into and out of an enclosed space, resulting from air buoyancy. This buoyancy occurs due to a difference in air density resulting from temperature differences inside and outside of the designated space. Results for this investigation were measured through recording the number of full spins the pinwheel made within the space of 1 minute. The constants for the investigation, meaning the factors that didn't change when the variables were tested, included using the same device each time, which was Mark III, the same window, angle and surface, and the device was always put in the sun for 20 minutes before testing, and then it was taken out of the sun for 20 minutes before the next variable test begun. This data was collected by colouring one corner of the pinwheel and noting each time it reached a specific position within 1 minute. These results were recorded and measured against one another to decipher which variables aided the usefulness of the tower most. To allow for simple assessment of data results, each variable was numbered. Number 1 was the control variable. This was the original test. With the control variable, the books set underneath the tower that allowed airflow were of a 3.2 centimetre width and were set 5 centimetres apart. Variable 2 was the same test with only the width of the book set under the tower changing from 3.2 centimetres to 4.5 centimetres. Variable 3 was similar except for the books set under the tower were smaller with a 1.3 centimetre width. Variables 4 and 5 were based around the distance between the books. Where the control variable had a 5 centimetre gap between the two books, variable 4 had a 6 centimetre gap, and variable 5 had only a 2 centimetre gap between the books that were below Mark III. As shown in Figure 1, the results were recorded and put into a table form. These results were then transferred into a clearer form to be assessed. It is shown here that variable 4 was the most successful variable, followed by the control variable. It is also clear that variables 3 and 5 were not successful. This means that the level of output for the updraft tower created in this investigation depends primarily upon two variable factors: the book width and the permissible air movement due to the space between the books underneath the tower. Overall, the results for this investigation show that placing the device on books that have a width of a 3.2 centimetre and have a space between them of 6 centimetres is the most effective way to produce energy with this system.